So today I want to discuss the same idea that I introduced last time of perturbation series and this Fredholm alternative idea as applied to differential equation. But first, before I do that, let me just summarize what I was trying to say and hopefully achieved to communicate to you guys last time. So suppose we have, I know I used Q last time. I may need Q for some other variable, so I'll keep Z here. So suppose you have an equation of the following form. L is something like a matrix. Z is a vector in Rn. Epsilon is a scalar. N of Z is some vector-valued polynomial function of Z. And we assume a perturbation series of the following form, and then the order 1 equations become this. So this L of Z naught is 0. And to get non-trivial solutions to this problem, we need L to be non-invertible. So L must have a null space, otherwise you don't have non-trivial solutions. So then so this can imply, let's say Z naught is some alpha times V when, let's say, determinant of L is 0, where alpha is again a scalar, V is some vector in Rn. Okay? So that can be the case, right? Where V is the eigenvector with 0 eigenvalue. Now the order epsilon problem will turn out to be necessarily. Right? So I have to pick up everything with an epsilon. So I'll get Z1 from the first term, and I'll get N of Z0, which of course I can write as negative N of alpha V. Okay, nothing done so far. Question is, what if the kernel is one-dimensional? Is multidimensional. So what if the kernel is multidimensional? Let me just consider a specific vector V. So let me consider a one-dimensional object for Z0. I could do multidimensional. A lot of the ideas extend, but just for simplicity's sake and to be consistent with every other example I will usually pick one special element out of the null space and then show how that element changes due to nonlinearity. In fact, in many of the problems, we'll see the null space will actually be higher dimensional. And I'll just pick one special element out of it. Now, to solve this equation, since L is non-invertible, you have to have this right-hand side in the right space. So there's the Fredholm alternative condition. But you also need, you also then will have an arbitrariness for Z1 because L has a null space. Right? So the Fredholm alternative will require that N of alpha V be perpendicular to all, let's say, Y, where L transpose Y is 0. Right? That's the alternative. It has to be, the right-hand side has to be perpendicular to whatever is in the null space of the adjoint. Okay? So if you think about this, let's write it in the following way. This is an equation for alpha. Because you know V, you know Y, and then that's an equation for alpha. Okay, so that fixes alpha. this implies that Z1 is going to be some particular solution plus, let's call it, or maybe let's call it alpha 1 times V, where alpha 1 is now an arbitrary parameter, right? Now, how do I find what alpha 1 is? You have to give me some condition. You could tell me, look for those Z1s which are perpendicular to the null space, in which case I will set alpha 1 to 0. Alternatively, you could say, go to the next order. Now your right-hand side will have an alpha 1. And apply the Fredholm alternative condition to find alpha 1. So every time you have an unknown parameter at one order, you need to go to the next order to fix that unknown parameter. Does that idea make sense? I mean, it's exactly how I fixed the original alpha. I had to go to order epsilon. Original alpha came as a degeneracy or an unknown parameter at the lowest order. I fixed it at the next order. If at the next order I have an unknown parameter, I need to go to one more order to fix it. So to summarize, then, this thing looks like an alpha V plus some particular solution plus an alpha, let's say epsilon, plus an alpha 1 V. Right? Yes? That this equation is not solvable. Right. So that's a good question. So what happens if that equation is not solvable? Then it basically says that there exists no such right-hand side that you can legitimately put here to solve. So then, from a physical standpoint, your problem is ill-posed. You've asked the wrong question. Right? So you really want to be in those situations when you can actually solve for that, that alpha. I mean, certainly one choice that I've sort of implicitly assumed that n of 0 is 0. So there's one choice that's available always to me. Maybe that's an uninteresting choice, but that depends on the context of the problem. Yeah. So if you look at what the structure of the solution looks like, it's an alpha V plus an epsilon alpha 1 V. So one could have actually added this term to the first term, and it would have been as though you had expanded the alpha itself in an epsilon series. Right? So you can take sort of dual ways of thinking about this. Either the original alpha itself gets expanded in an epsilon, or you have a degeneracy at each order, which helps you sort of enforce a condition at a next order. So you want to have enough degrees of freedom to keep enforcing a condition. That said, from a strict mathematical point of view, and even from a sort of a practical point of view, you never really go this far out. You usually just stop with the first term. Calculations get very, very tedious. Thank you. So, of course, if you were trying to prove a theorem, what you need to prove is basically this series converges. And in the example I gave last time, you can actually rigorously prove that the series converges. In some of the examples I'll discuss today, that gets a little harder. One can still do it in some cases, and in some of the examples I will discuss, it's just, we just don't know. And there's a lot of hard work to actually prove that these things work. Okay? All right. Okay, so I want to sort of keep that in mind, and that's going to be our sort of framework to talk about these things. So the problem I want to discuss today is the one I hinted at the end of last time's lecture, this nonlinear oscillator, d squared y dt squared y plus epsilon y cubed is 0. And we wish to, so our goal is find periodic solutions. So functions y of t that are periodic, I don't know the period. In fact, the period itself is something that has to come out of the problem. Okay? So I can certainly write it in the form of a system, ddt x1, x2, 0, minus 1, 1, 0, x1, x2, plus epsilon 0, x1 cubed, 0, 0. So little bigger? Sure. Good? Okay. All right, so we want to find periodic solutions to this. Let's just first sort of convince ourselves that's a reasonable thing to ask by actually answering the question completely. And then do perturbation methods as a way of sort of getting the answer in a different way, which will work in a different context, where we may not know such things exist. This is kind of like a Newton's equation. There's a second derivative, and there's a potential. And it's not too hard to show that this is actually representative of a Hamiltonian system. But the more important thing is ddt of, let's say, dy dt squared with a 1 by 2 plus y squared by 2 plus epsilon y to the 4 by 4 is 0. Right? So there's this conservation law that you have, which reduces your problem to a first-order ODE, which you can then sort of integrate explicitly in terms of elliptic integrals. Leave that aside. But the point is, at least in the y dy dt plane, you can draw closed loops which represent periodic solutions. So periodic solutions in the phase plane exist. They only exist for certain choices of the total energy, not for all choices of the total energy. But leave that aside. The point is, this problem certainly has periodic solutions. So it's a reasonable thing to ask. Okay. I'm not going to get into any further detail about that. So here, my L operator is ddt plus 0, negative 1, 1, 0. And this is what I'm calling, let's say, n of x1, x2. Right? Okay. So what's the logic? We would like to use a perturbation series. And in order to proceed, we need to know what the transpose or adjoint of L is. Right? We need to find out what the null space of the operator is, and we need to find out what the null space of the adjoint is. That is transpose. Right? So I need to know what the null space of this operator is, which is to say, this acting on something equals the negative of this matrix acting on something. So this is a constant coefficient ODE that you can certainly solve using, in this case, diagonalizing the matrix, writing down the eigenvalues, the eigenvectors, so on and so forth. That is done in the notes, or at least the idea is sketched out. I'm just going to write down the answer. Yes. Say that again? Huh. Oh, okay. So let's interpret this condition. What does it mean to have determinant of L be 0? What it really means is there are non-trivial solutions to this problem. So understand this condition as, do there exist non-trivial solutions to this problem? If you can answer that question directly, don't even bother about what you mean by determinant of L being 0. Clearly, determinant of unbounded operators is a more subtle question, and I'm not going to get into how to define that. I just want to know, is there a non-trivial vector that if I multiply here, I get 0? And that's certainly true, because in some sense, the linear part is actually this second-order equation, like d squared plus 1. Yeah, sure, there are non-trivial solutions, sines and cosines. Right? So, null space of L, where do I write that down? Is 1I e to the it 1 minus I e to the minus it. So the null space of L is spanned by two vectors. 1I and 1 minus I are the eigenvectors, plus or minus I are the eigenvalues for this matrix. And so if you take this vector, act it on with L, you will get 0. If you take this vector, you act it on with L, you will get 0. Okay? Yes? Mm-hmm. No. The simple answer is no. So you're asking if I choose initial conditions such that if I choose the initial condition to be 0, does that say something about the operator? No. No. Choosing the initial conditions doesn't say something about the operator. And as I pointed out, understand the determinant L equals 0 condition as the existence of non-trivial solutions to the homogeneous problem. Are there non-trivial solutions to the homogeneous problem? I've just written down the null space. The determinant L condition makes perfect sense for matrices. Obviously, for unbounded operators, it's a more subtle issue. So we go down to what actually you want. You don't want determinant of L equals 0. That's sufficient to guarantee the existence of a non-trivial null space. Is there a non-trivial null space? Yes. Moving on. Okay? All right, so I have this. I would be interested in real valued solutions, so maybe I do this. Yeah? I can take this linear combination for real valued solutions. One of them should be multiplied by an extra I. I agree. But clearly, I can do that. Okay. All right. Now the question is, what's that? Because I also want to know the null space of the adjoint. Okay? So to define the adjoint, we need, well, I need an inner product. Okay? So let F be some vector F1, F2, let's say these are functions of time, and G be another vector be, let's say, tau periodic functions. two functions, two vector-valued functions that are periodic with period tau. Okay? The inner product I'll define as the integral from 0 to tau of f1 of t, g1 of t, plus f2 of t, g2 of t, dt. Take the Euclidean inner product, integrate over time. That's all that is. Okay? So, the definition of L transpose is F LG should equal LFG for all FG. You have the definition of L, you pick an F and a G, and how do you go from here to here? Integration by parts. Right? So you're going to have a matrix multiplying the vector, as well as you're going to have this DDT. This DDT will turn into a negative DDT when you do integration by parts. There'll be no boundary term because everything is assumed to be tau periodic. Okay? Everyone okay with that? I'm not going to do the calculation. I'm just going to state down what L transpose looks like, or the adjoint. But it's a simple exercise in just moving stuff to the other side. Okay? Also, this matrix will effectively be transposed, because this looks like F transpose multiply, like it's F transpose G. Right? So if you move the matrix from the function to the other, from the vector to the other side, it'll become a transpose. So with that, I'll just say this is minus ddt plus, where is it? There. 0, 1, minus 1, 0. Okay. That's all that is. Notice L transpose, or the adjoint, looks like negative L. Everyone agree with that? L adjoint looks like negative L. I have the null space of L. I have the null space of L adjoint. It's the same thing. The span of these vectors is the same thing. Okay. Boundary term. When you do integration by parts, boundary term. By L prime, you mean the adjoint? Yes. Yes. Inner product comes with a space, with boundary conditions. Yes. So I'll come back to that point and hint at why this is a non-rigorous calculation eventually, because I will be very fast and loose with certain kinds of boundary terms. But precisely because the inner product requires a specific choice of boundary conditions, and the heuristic calculation that's usually done in this style of mathematics plays fast and loose with the boundary conditions, and that's what makes it hard to make it a rigorous mathematical argument. Nonetheless, it is possible to make it a rigorous mathematical argument, but that's the difficulty. That's what you have to deal with. Okay? Sure. It doesn't go to 0, it's periodic. L2 on all time, as in L2 of R. But I haven't assumed that. No, I've assumed L2 of periodic. Yes, but okay. It's certainly true that if I had assumed the boundary conditions of vanishing at infinity, I would get the same inner product, or I would get the same adjoint, but it would be acting on a different space. And that will come back to bite you at some point. That will come back. And again, just hold that thought. Even with this periodicity, I'm going to have some trouble. So you can imagine the kind of trouble you will have there. And I'll come back to that. It's a legitimate question. But let's just take it for now that this is my assumption, guided by my goal. And then I'll see how good or bad that is. Any other questions? No? You substitute here, and you want it as the form of some operator acting on F. So you have to move all this operator to the other side. And that's effectively doing integration by parts. And sort of rewriting things as though they were being acted on by the function, on the function f rather than the function g. That's why you get the minus sign here. Okay, so this has the same null space. Which is, let's say, span of this 1I e to the IT. Yeah, is that what I wrote? Yeah, 1I e to the IT, 1 minus I e to the minus IT. Now, if I do the span over all complex numbers and I choose them appropriately, it'll still represent real valued functions. There's only a slight benefit for me to consider complex numbers, just so that I can compute this cubed really easily. E to the IT cubed is easier to do than sine of t cubed and then write that in sine 3t. I don't want to get into that business. But I'll make sure that my inner product is only defined for real valued functions, so I'll always have plus a complex conjugate. Okay? All right. Okay, so with this part resolved, we can actually write down the order 1 equation. Right? I know what L is. This is my order 1 equation. I know what my null space is, and I can write down my 0th order solution in this form. Okay, so let's start the perturbation series. So I take x1, x2 to be x1, 0, x2, 0, plus epsilon x1, 0, x1, 1, x2, 1, so on. And then this gives me the order 1 equation. Maybe I want to write both of these together. I don't need all this. Okay, so order 1, ddt x1, 0, x2, 0, plus 0, negative 1, 1, 0, x1, 0, x2, 0 is 0, 0. And then the order epsilon equation, ddt x1, 1, x2, 1, plus 1, negative 1, 0, 0, x1, 1, x2, 1 will equal minus 0, x1, 0 cubed. Everyone good with that? Okay. can get rid of this as well. So I have a perturbation series. These are my two equations. I can immediately write down x10, x20. I will take to be alpha 1I e to the it plus complex conjugate. As the point made earlier, the null space is two-dimensional. I'm picking a particular element of the null space. Okay? Also, just a point of notation, when I write plus CC, it only applies to the immediately previous term. So I might write something plus something else plus CC. That just applies to the plus something else. Okay, so think of plus CC as an operator that acts on the left. Okay. Alpha is complex. Alpha is complex. I mean, it can be, right? That's a real valued function. So this clearly is a 2π periodic solution. And we could stop it here. We say, hey, I found an approximate periodic solution to this problem. It's 2π periodic. And that's it. Okay? It's an approximate solution in that it doesn't satisfy the equation entirely. But I will also claim it's an approximate solution in that the period is only approximately 2π. Okay? All right. So now let me come to the order epsilon equation. I now know what x10 is. x10 is just alpha e to the it. It's the first term. Yes? Because it can be. It can be, and it's good to keep it. We'll see. But you certainly agree, in all generality, it can be. So you imposing it is real is making a condition that is at least not warranted at this point. The only thing I warrant is a real valued solution. I don't warrant alpha to be complex, alpha to be real. I would say assuming it is real is not necessary. The more general condition is that it is complex. You making the assumption that it is real is making a particular assumption because every real number is complex. Right? Why did I not write 1 minus I? Homework. Do everything that I do for that one. It's there in the exercise as well, in the notes. Okay. All right, so I need to solve somehow this equation. So let me first compute what this nonlinear term looks like. And this is nothing but 0 alpha e to the it plus cc cubed with a minus sign. Right? This is the only advantage of writing alpha e to the it plus cc cubed, because now I can use binomial theorem as opposed to having written it as sine t cubed and then having to write it in terms of sine 3t and sine t. That's the only advantage. Okay? Cool. Do I dare write this out? Probably not. I don't think I'm confident of myself doing that. Okay, let's just leave it as such. Good. What do we need to do at this stage? We need to make sure that the right-hand side to this equation is in the right space. We need to make sure that the right-hand side is perpendicular to elements in the null space of the adjoint. We have elements in the null space of the adjoint. So we need to make sure that this object is perpendicular to both. Right? Now, of course, you might say, no, you should take complex conjugates, special, real valued stuff. Sure, but the inner product is linear in each term. And so me making it perpendicular to each one of these things will make it perpendicular to linear combinations of these as well. Right? So I don't have to worry about that. Okay? All right, so now we need 0 alpha plus alpha e to the it plus cc cubed to be orthogonal to 1i e to the it and 1 minus I e to the minus it. Orthogonal in what sense? In the sense of my inner product. So I have to take an Euclidean inner product and then integrate over time. Right? I'm going to integrate over time. Which time? Over 0 to the period, which is 2 pi. Okay? So what's going to happen when I take an inner product here? The nice thing is, of course, that first term goes away. Great. 0 times e to the it. Wonderful. That's 0. I times e to the it times this junk. If you expand the cube, you're going to get an e to the it, you're going to get an e to the 3it, you're going to get e to the minus it, and you're going to get an e to the minus 3it. Those are the only options you'll get. Because of this, it's this complex conjugate, right? So if you take 2 of these and 1 of these, that's an e to the it. If you take 1 of these and 2 of these, that's an e to the minus it. And if you take 3 of these, you get e to the minus 3it. Everyone okay with that calculation? Okay, so when I expand this, I'll get a e to the it, e to the 3it, e to the minus it, and e to the minus 3it. And each one of them will be multiplied by an e to the it here, when I take the inner product. So if you write down this integral, so the inner product, so this is equivalent to, let's say, I e to the minus it alpha e to the it plus complex conjugate cubed dt is 0, and should also be 0 to 2 pi I e to the it alpha e to the, let's put a minus here, although it makes no difference. Consider the term that's e to the 3it. Gets reduced by 1, e to the 2it, integrated over 0 to 2 pi, 0. E to the minus 3it, multiplied by a minus it, e to the minus 4it, integrated over 0 to 2 pi, 0. E to the minus it times e to the minus it, e to the minus 2it, integrated, gives 0. But there's an e to the it here, that multiplies by e to the minus it here, and that becomes 1. And then that's average is not 0. So let me just write down what that implies. How would I get to the it here? I need to take 2 of these and 1 of these. So that's alpha squared alpha complex conjugate. Should equal 0. Should equal, play the same game here, but it'll be the other way around. It'll be alpha complex conjugate squared alpha. And you can see the problem. Alpha has to be 0. Okay, well, what does that mean? That means my solution is 0. I want lots of confused faces at this point. 1 second. What is tau? I have to fix tau. Tau in this case is the period of the functions. Why? Tau is, let me come back to that. You know the answer. You were there in my class, so you know the answer. So I'm not going to answer your question. What's your question? No, I just wanted to deal with real valued functions. No, 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 no. Do that as a homework. Yes. Yeah. And add the set of solutions to that two equations would be 0, 0. Try it. Any other question? As should be said, shh. No. No. Yeah. Yeah. No, a real value data product exists. Fine. You could have taken the plus the complex conjugate here. But if the inner product is linear in this term, and you would have minus plus the complex conjugate here, and you could add and subtract those two equations and come back here again. So there's no way around that fact. Because the inner product is linear in those two functions, I can either take linear combinations of these or just these. If all I need is you should be perpendicular to the whole space, I can take actually any basis vector, any set of basis vectors that are independent, whether they are complex valued or real valued. Because they're independent, I can reduce one to the other. So it seems like I'm cheating. I'm not. No, but so if you were to take, I mean, you have to be careful about what your basis is. So I'm doing this for convenience of notation, given the fact that I could have used real valued functions and it's still a 2D space. So if I restrict to the fact that it is real valued, that's where the extra set of equations come from. So then it's not 4D, it's 2D. Okay. Any other questions? So we all agree this is a problem. Alpha is 0, and so then there's no solution. So now we need to do something. This is different from what happened in the case of the algebraic example I considered. In the algebraic example I considered, you ended up with a quadratic in alpha that you could solve. Here, we started off with an ODE and ended up with an algebraic expression. So I'm going to heuristically motivate that this should not have been an algebraic expression, but an ODE for alpha. Why should alpha be a constant? Why can't alpha be a function of time? You might ask, well, why would you ever do that? Well, how do you solve non-homogeneous problems? One way is variation of parameters. And what do you do in variation of parameters? You take the homogeneous solution and you take the constant multiplying the homogeneous solution and you say, let that be a function of time. So let's play the same trick. Let the constant multiplying the homogeneous solution be a function of time. So let me turn this alpha into an alpha of t. Okay? Now, what would happen, just imagine, what would happen if it was alpha of t? Well, it should still satisfy the order 1 problem. So if it was just generically alpha of t, it won't actually solve the order 1 problem because this time derivative will also act on the alpha. So if it was just alpha of t, you'll have a d alpha dt over here. And so it's not an exact solution to the order 1 problem. So my requirement is that I want to turn alpha to a function of time, but I want to make sure that this is still the order 1 solution. The problem, as I said, is the fact that when you plug it into the order 1 equation, you get a d alpha dt. So I want the d alpha dt to not be there. I could set d alpha dt to 0, but that brings me back to here. And this is where I realize set d alpha dt to be order epsilon. Because that's all you need. You just want to make sure it's not here. It could be here. Right? So, the way out, so this obviously implies alpha is 0. Alpha is alpha of epsilon t. So that when you differentiate with respect to t, you get epsilon alpha prime. And so that can't appear in this expression. It has to appear in this expression. All good? Yeah? So sometimes we call this the slow time. This t is the fast time. Okay? Does break periodicity. And that's why the period changes. So it won't be 2 pi anymore. There'll be a correction to 2 pi. Coming back to his question, getting rid of my punchline that the period will change because alpha will have its own period. And then there'll be a total change to the period. We'll see that. Okay, so let's call epsilon t tau the slow time. Tau. Okay? So this is why the method is called the method of multiple scales, multiple time scales. Because you naturally introduce a degree of freedom to get yourself out of a situation. Okay, I have colored chalk, so let me use colored chalk. So what's going to happen if I replace this with alpha of epsilon t? This is still the same order 1 equation by construction. But the order epsilon equation has to now change. I will get the time derivative acting on the alpha times that same vector. So let me put that to the other side. So I'll get minus 1 e to the it d alpha d tau. No, it'll be no, because it's the same L. L hasn't changed. L hasn't changed. But I have a degree of freedom to make sure that alpha squared alpha bar doesn't have to equal 0, but can equal d alpha d tau. So tell me how alpha should change so that there's no component in the wrong direction. Okay, so the question is, why did I assume an epsilon here, not an epsilon squared or an epsilon cubed, so on and so forth? Suppose I assumed epsilon squared. Well, I wouldn't get this term here. So then I'd have the same problem, and I wouldn't actually solve my problem. So how can I make d alpha d tau appear here? Well, the only way is it should have d tau dt should be epsilon. In a more complicated problem, the answer is probably yes. In such a problem, it's fairly obvious that if you assumed any other power, you would have no degree of freedom. Okay? All right, so we already sort of computed what this would be. By the way, I should actually have a 3 here and a 3 there. But the 3 doesn't matter. But the 3 matters when I don't set it equal to 0. Right? Okay, so now when you apply the orthogonality condition, so the Fredholm alternative applied to the thing in the yellow circle now gives me 2 d alpha d tau is 3I alpha squared alpha. Okay, I'll leave that. It's in the notes. Leave that for you to check. Very good question. Very, very good question. I wanted to sort of sneak that in and then bring up that point. So it's an absolutely good question. Previously, when alpha is a constant, I can just do the integral over 0 to 2 pi. How can I get this if I'm doing an integral over the new period? Because alpha is a function of time now, right? So if you considered this integral, for instance, this is the one that you really have to worry about. If you consider this integral, alpha is a function of time. So it can't really just come out. You can't just say, oh, you have an e to the 0. That's the one you have to worry about, right? So let's actually sort of write that out. Let me actually write that out here. If we now do this, I will get 0 to tau minus I e to the minus it alpha of tau e to the it plus complex conjugate cubed dt, where tau, remember, is epsilon t. And then I'll get minus, I'll get again a minus I e to the minus it, I d alpha d tau. Let me put it this way. I think all of this just becomes, what is it, 1I and 1 minus I. So we'll get 2 e to the minus it d alpha d tau dt 0 to, so some period. Let's call it, let's not confuse ourselves. Let's call it some period. Equals 0. So that's what I'll get. That 2 comes from the fact that it's 1I, 1 minus I. That's all that is. Okay? All right. So to go from here to here, I've effectively pulled all the alpha terms outside of the integral. Okay? What's the cost of doing that? There's actually an error. You can't just pull the alpha out. Alpha is a function of time. You can't just pull it out. On the other hand, alpha only depends on epsilon t, not on t. So if epsilon is small, maybe you can Taylor expand alpha about its constant value, where it hasn't changed much, and then add a correction, which will be proportional to the first derivative, which is epsilon. So I'm making an error, but I'm making the error at the next order. So what I can do is, so far as this integral is concerned, alpha is a constant. It's kind of like saying there are 2 timescales and you're averaging your data over the short timescale where the other thing hasn't really changed. So you're averaging over the high frequency to get the slow behavior. You are making an error, but the error you make is proportional to the rate of change on the slow timescale, which is a higher order effect. So what does that mean? My period should actually be 2 pi. Don't keep the period on the large time scale. Average over the oscillations on the fast time scale so that alpha hasn't changed much, so that you can pull alpha out and make an error that's at the higher order level. Of course, when people do this, nobody ever mentions this. They just pull it out, and then they say it. That's kind of what makes proving this as a rigorous mathematical statement difficult. Because you are making error. You're making error at a next order level. You're not telling anyone, and you're just stating a result. Now, I can share a PDF with you guys from the book called Bender and Orzag, where they actually do a high-precision numerical simulation of this problem and show the asymptotic result as well. And it's unbelievably accurate. I mean, it has no business being that good. So, yes, we are making error, but surprisingly, it turns out that the error is not as bad as you think it is. Okay? Rigorously proving that statement, not going to get into, not the subject of this talk, but the subject of the talk is certainly to sort of indicate what the logic is. So the logic that forced us was we needed a degree of freedom. We allowed that degree of freedom by saying, okay, that which was a constant, let it be a function. Previously, in the case of the algebraic example, we let it be a function of epsilon. Now things are functions of time, let it be a function of epsilon and time. Choose the right dependence so that the term appears at the right order so that you can save yourself, prevent something bad from happening. But then when you apply the orthogonality condition, keep the period this. Many of these things for this particular problem have been rigorously established with error estimates. So that's not an issue. But certainly how you sort of view these things, where the heuristic is coming from, is the fact that there's something happening at a very fast timescale, and you're saying, well, on average, that all cancels out, and then there's only the slow behavior. Okay? Let me come to that. So the question is, what's the connection to the period? Let me come to that right now, okay? So this is a logic that we will follow throughout, which is whenever we take an inner product, we will always assume slow variables to be constant with respect to the inner product. There was a question about spaces, that the inner product needs a certain period that defines a certain space. In a more strict mathematical sense, I've kind of jumped out of the first space and gone into a bigger space, but making the operator L still act on the original space, because it still has the same period 2 pi, even though the function now may have a different period. And so that's another reason why the mathematics is a little more difficult, because I'm playing fast and loose with my spaces. Fast and loose in the sense that integrals with respect to little t are always over 0 to 2 pi. Things that depend on tau are considered constants, even though the original solution clearly has dependence on both. So in the method of multiple scales, people usually phrase this as the two timescales are independent variables. Tau and t are to be treated as independent variables. And of course, in that logic, if tau and t are independent variables with respect to differentiation, they would also be independent variables with respect to integration, and hence things can come out of the integral. Right? Question? Yes, 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 100%. So these are good approximations to the true solution up to a certain time. And that's the kind of theorem you can only prove. Yes. So the question is, if you have inherent stability, that means you added a new structure to the problem. You gave me a new tool to exploit. For instance, perhaps the structure is there exists a conserved quantity. But that's a global statement. And perturbation theory may or may not know about the existence of such global quantities, which is another reason why perturbation theory is usually seen as a heuristic and not rigorous, because you're not using all available structures and it's not able to detect all possible structures available to exploit. So for instance, since I have a conserved quantity, I know things exist on a level set. So I know things can't get too large. And in this case, I can probably bound it in phase space. You must be within this ball. And so then errors can't get too bad, right? But that's an extra piece of information that I don't have at this level. So we like perturbation theory because it allows us to do problems which may or may not be Hamiltonian, but we may or may not be able to get the same level of guarantees when the problem is Hamiltonian. I mean, come on, life can't be that easy, right? Okay, so it's not too hard to show that if I multiply this by alpha bar and add the complex conjugate, then the right-hand side vanishes. If you multiply by alpha bar, you get alpha absolute value to the power 4. There's an I, so it goes to a minus I. When you add the two, they cancel. So what that means is dd tau is actually 0. Alpha bar d alpha d tau plus alpha d alpha bar d tau is dd tau of alpha squared. There are some confused looks. Is everyone okay with this? This fact allows me to actually replace this by the constant, the initial condition. So then this says absolute value alpha squared is a constant. Let's say alpha naught. And then I can immediately integrate this equation, because then this is a linear equation. Okay, so then I'll just write down what alpha is. This says alpha naught e to the 3 alpha naught squared I tau by 2. Okay? So, in this case, it turns out I can actually write down what alpha is. So I can go back over here and write down my solution, x1, x2, to be alpha naught e to the 3I alpha naught squared by 2 epsilon t, 1I e to the it plus complex conjugate plus order epsilon. So I just substituted what the function alpha is. Everyone good with that? Now combine the two exponentials. And notice that this is a problem with a different period. So there's a correction to the period. There's an epsilon correction to the period. This has a period 2 pi, and there's a correction to the period. And that correction to the period is a function of the amplitude of the solution, because it depends on alpha naught squared. Okay? Now, if I wanted to compute what this correction was, I could now go back to this equation and solve for x1, 1, and x2, 1, if I wanted to. And I encourage you to do that. You will get a particular solution which will depend on this type of an exponential plus a homogeneous solution. And that homogeneous solution will have an arbitrary parameter, which will only get decided when you go to the next order. But make sure that that arbitrary parameter is a function of time, because you won't want an algebraic equation for the arbitrary parameter. You will want a differential equation for the arbitrary parameter. Which function of time? Not epsilon t, because if it was epsilon t, this equation wouldn't remain the same. So it has to be epsilon squared t. Okay? So then you naturally see that you're going to allow alpha naught, for instance, to vary on a yet slower time scale. That's what it will be equivalent to be. Okay? So that which was a constant starts depending on time. Which time? Slower than all the times you've seen so far, so that nothing gets mucked up when you go to the next step. and so that you have a degree of freedom available at the final step to enforce the Fredholm alternative. So you successively do this, but usually people just stop at this level. Quite often, this itself is a remarkably good approximation if there's some additional structure helping you along the way. So these type of problems tend to produce remarkably good approximations. Okay? Any questions about this? Sorry, you have to speak louder. What fixes alpha naught? At this level, alpha naught is arbitrary. What fixes it is when you go to the next level. There are no initial conditions. We're demanding periodicity. Right? So long as I work with exponentials e to the I something t, I'm going to deal with periodic functions. So you can see what's going to happen if you go to further and further higher orders. You're going to get different numbers here. You're going to get different numbers here. You're going to get different exponentials here. Let's think about what all the possible exponentials you'll get. Clearly, I have an e to the it at lowest order. This guy on the right-hand side is going to have an e to the 3it. So there'll be a particular solution with e to the 3it. I'll also have a particular solution with e to the minus 3it. Right? Because I'll have an e to the minus 3it here, so I'll get a particular solution with an e to the minus 3it. That's the usual story people tell about nonlinearity. Start with one mode, generates higher modes. Start with e to the it, you get e to the 3it, e to the minus 3it. What people don't always tell you is you also change the amplitude. Not just you introduce new frequencies, you change the amplitude. Alpha, the amplitude changes. But it doesn't change at the same time scale of t, it changes at a different time scale. So what nonlinearity tends to do is not just introduce higher harmonics into your problem. You don't just have e to the it, e to the minus 3it, and then from there on you'll have combinations of 1 and 3 cubed, so that'll give you 4, minus 4, so on. Not just that, but the amplitude itself is changing on a different time scale. So nonlinearity screws up both things. And it does it in a very delicate way in that if you have this degree of freedom epsilon, it changes the amplitude slowly, and it introduces high frequency quickly. And sometimes in a physical experiment, like an electric circuit, you can actually model these things and sort of see higher harmonics appear, and then slowly those higher harmonics have an amplitude that's modulated. Because what this is a modulation of the frequency 1. Right? So nonlinearity modulates and introduces higher frequencies. Effectively, it's producing integer multiples of 1, and it's producing rational multiples of 1 for the amplitude. Now, maybe there is a lowest common multiple of all of the rational numbers you have, and that's the period that you can sort of determine. What is the period of the full solution? It's the period at which you are periodic with 1, you are periodic with 3, you're periodic with 3 by 2, so on. Yeah, so there's a total possible period. And clearly, as you add more and more terms, you have to go to higher and higher powers of e to the it and whatnot, and you see that you get more and more complicated looking signals. Which is to say, for a weakly nonlinear system, when you wait a long time, you start seeing behavior at different timescales. You start seeing new harmonics, and you start seeing new modulations. Yes, absolutely. That's what makes it nonlinear. So one way to think about what a linear problem is when the amplitude doesn't matter. Because a linear problem is homogeneous of order 1. So amplitudes don't matter. A nonlinear problem precisely breaks that symmetry. And so then your dispersion relation is actually amplitude dependent. Because my period here is amplitude dependent. And that's exactly what nonlinearity does. It mixes up amplitudes and frequencies. And in PDEs, we'll see that usually the wave number will determine the frequency, and then the nonlinear correction will make the frequency change as a function of wave number and amplitude, as here. So in that sense, turning this to a PDE doesn't really introduce too much level of sophistication. You have something that's spatially periodic with 2 pi, and let's say temporally periodic with something, well, then that period will change because of the amplitude. Can you still what? Can I still define the energy? Yes. I mean, I can compute it. But amplitude oscillates, but it doesn't grow. The amplitude value is 1. Right. This is, as far as I've written, I don't have anything with a t. I have only exponentials. So this is a perfectly bounded solution for all time. So where is the error with respect to the true solution? It's a very good question. It's in the phase. It's in the fact that my period is wrong, not in the fact that my amplitude is wrong. My amplitude is 1, and for the full problem also, it's the same number, but what's wrong is my period. So what you'll see is that the asymptotic solution and the true solution are on top of each other, and then they start separating in phase. The true solution is a phase apart by some angle, and then that angle gets worse and worse. And how quickly you see a phase error depends on how far out you want to go. Right? Now, this is all hand calculation, so you rarely go far out at all. But if you are developing a computer algorithm, then maybe what you would do is do a restart and choose the current initial condition, like modify the initial condition and do a restart. Don't start from, it's almost like estimate the phase error, find out what the true condition or an estimated true condition should be, and use that as the initial condition to march ahead. Some people have done numerics inspired by that kind of asymptotic analysis. On the other hand, what you could also do is make something like add a correction to this thing, and then demand that it satisfies the ODE on a longer time scale, and find out how the period should change. It's like some sort of parameter estimation, an optimization problem. And you can repeatedly do that and get better estimates. And at that point, it turns into effectively doing Newton's method to find the period of the solution. That's literally what that is. So all perturbation methods is basically setting you up to do Newton's method, but by hand. If you coded this up and said, let me figure out how the period should change so that it's still a solution to the full problem, then that's Newton's method. Correct. Correct. Absolutely. So this is a perfectly valid function, but it's just not a solution to the original problem for all time, which is the point Sumit raised, is that your estimate on the error degrades with time. So you need further corrections to get the estimate smaller. So typically the type of theorem you can prove is, I want an error to be bounded by a certain amount for a certain time. How should I fix the period? Can this process be extended term by term indefinitely to guarantee such an error estimate? For a problem like this, it's not too hard to do those things. So I think, what I'm presenting is not original work. This stuff was done in the 80s and the 90s, the rigorous proof. The asymptotics was done probably even before that. So for these type of ODE problems, we know a lot about how to look at these type of things and how to rigorously prove it. For the PDE stuff, over the last probably 20 years or so, people know a lot more, and you needed a lot more sophisticated tools to show at what time scale is this a good estimate. So maybe you start off with something like shallow water equations originally, and then say, I want to approximate this by some simpler model, something like quasi-geostrophic equations, and then at what length scales and time scales is a solution to the quasi-geostrophic equation also a good solution or an approximate solution to the full shallow water equations? That's a theorem that people have certainly attempted in different contexts for different types of approximations, different types of models, and always it is up to some time. Close to t equals 0. No, I'm looking close to tau equals 0. Tau being 0 doesn't mean t has to be 0, because it's epsilon t. T could be 1 over root epsilon. It could be a large number. Still, I have another root epsilon left. So it's saying I'm short on a long time scale. Which is another point I want to emphasize. If your problem doesn't have separation of timescales, this is not going to work. So for instance, I don't want anyone asking me, this work for turbulence? No. Okay? It won't. When you have coupled length scales and time scales of 2 different orders of magnitude, this is not going to work. The whole point of this epsilon business is to say that something is happening at one time scale, something else is happening at another time scale. If these 2 things are happening at the same time scale, that's a legitimately nonlinear problem. Let's flip the thing. This was all about weakly nonlinear equations. What do I mean by weakly nonlinear equation? There exists a separation. There exists a separation of time scales. If there doesn't exist a separation of time scales, it's not weakly nonlinear. What is a linear problem? Each time scale evolves on its own, because there's no coupling. Nonlinearity introduces the coupling. What does the coupling do? The coupling introduces higher harmonics and modulates the amplitude at a different time scale. I mean, formally, you could say let epsilon be 1. Sure. Is that a good approximation? It depends on the additional structure you have. For some problems, you can prove that if you get an answer at 1 epsilon, you can rescale it and get an answer at another epsilon for free. There's an epsilon scale invariance, in which case, great, wonderful, use that. But that is another piece of information that I didn't start off necessarily with. Right? So if you want more, give more. Bare bones perturbation theory is just going to give you some asymptotic series, and then how good is it really depends on the details. But what is true, and this sort of introduction of modulation of amplitudes, that's actually a very useful insight to pull out, that what nonlinearity does, it doesn't just introduce higher frequencies, it modulates the amplitude. Or at least it can in a whole host of equations. So if you start off with one profile as a solution to a problem, maybe that profile changes slowly on another time scale because of a nonlinear effect. This ODE to alpha depends on an arbitrary parameter, alpha naught. Alpha naught is a constant, but only on the tau time scale. Epsilon squared. Epsilon tau or epsilon squared t, possibility. So I have a degree of freedom that I could assume alpha naught to be alpha naught epsilon tau. But I will leave it arbitrary if I stop here. I will define what that is if I go to the next order and figure out the Fredholm alternative condition at order epsilon squared. In practice, nobody ever does that. Mostly because at some point when you take a course in this, an instructor will give you an assignment to do that, and you will never want to do it ever again. So, I mean, maybe I should assign that homework. Go ahead and do that, learn it once in your life, and say, I never want to do this ever again. Sure. That's also why I did that. Hey, there's a Hamiltonian. There are clearly repeated cycles, so things can't get too bad. But you may or may not be able to detect the non-existence of a periodic solution using perturbation theory. One way in which you may be able to detect goes all the way back to the question Anish asked, which is, how do you know you can solve for alpha? So when you had this condition that you wanted to enforce the Fredholm alternative, maybe you realize, I can't. And maybe that's because there are no such solutions to be found. But unfortunately, just because that doesn't work, that you cannot solve for alpha, doesn't mean anything. It just means it doesn't work. You don't know what reason it doesn't work for. So then what you do, you look at everything you see, wherever you've made an assumption, wherever you see a free parameter, you say, let that change. You're like, oh, I said periodic. Maybe I don't mean periodic. Maybe I mean quasi-periodic. So you go back everywhere, you made an assumption, everything that was a constant, you say, let that also change in epsilon. You keep doing that till you have enough degrees of freedom to make sure that that damn thing actually has a solution. An interesting solution, not zero. If you fail repeatedly, you move on to a different problem. And at some point, you have to give up. Not straight away. But at some point, if it's not working, you need to do something else. But the logic usually is degrees, anything that's a constant is up for grabs. So for instance, maybe that was a constant. It was a constant 1 previously. Let's replace it by a function that I don't know, and let's find the function. Usually that's what you do in a method called WKB. Usually that works only for linear equations. But it turns out I could have repeated this entire analysis and fixed the period to be 2 pi always and found the correction to the function omega. Because clearly, omega carries the information of the frequency. And so I can say, yeah, it starts off at 1, but it has a perturbation. So you can start doing things like that as well. And you sort of want to give yourself enough degrees of freedom to overcome these obstacles. So I started changing the period, but kept the period here sort of heuristically 2 pi and said I'm making an error. I could have said there's an unknown function omega that you have to find along the way. That's your degree of freedom. And what is an approximation to that omega? 1 plus epsilon 3 alpha naught squared by 2. And that's related to that omega squared. So the question is, if I'm not doing this entire thing, what would I have done? Something else. No, that's not true. That's not true. So it's not true that it only works when we're looking for periodic solutions. I don't want to say when it all works, because it's usually case by case. So it can work, as someone mentioned, when you're looking at problems on the whole line. Typically, I will do that when I have a spatial direction as well. I won't always look at problems on the whole line for time. I'll usually look for time periodic solutions. I mean, if you have a problem which is rapidly decaying to 0, don't do this, just decay to 0. That's your asymptotics. You go to 0. If you're interested in the approach to 0, then what you do is you sort of expand everything around t equals 0, and then maybe you get some oscillations, which are modulated on a longer time scale, maybe. So that's like a viscous damped problem. Like some sort of viscous oscillator, something like that. Possibly. But as I said, in order to actually be able to prove that your approximations are good, usually we'll work with conservative systems. Because conservative systems afford me something like an NRT, a Lyapunov function, something that I can control the size of the solution with. And you may already know this, Hamiltonian systems are basically things that oscillate. At the best kind of Hamiltonian systems are basically things that just oscillate. So you start working as a perturbation of a system that is integrable. And that's exactly what I took. I took a perturbation that's integrable. It happens to be an integrable perturbation, but I certainly started off with a system that is an integrable Hamiltonian system and perturbed it by something, and then saw how do the frequencies of the oscillators change. So a more rigorous version of this is literally what some of you may know as the Kolmogorov-Arnold-Moser theorem, because that's really what you could do as a perturbation calculation if you made that perturbation calculation rigorous. Making it rigorous is the real fun part, or the hard part, depending on how you look at it. But the intuition is almost exactly the same. Yeah? Yes? Okay. Yeah. Yes. Yes. Some numerics or something, yeah. For some time. For any epsilon, there is a time up to which it is good. No. No, because that just determines alpha naught at this level. That just determines alpha naught. In terms of initial conditions, no. 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 Yeah. 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 Yes. And then you see a gradual phase error. So the two sinusoids start separating in phase, but not in amplitude. After that time. So that means their amplitude is exactly the same. Yeah. So the time, the time at which, yes. Correct, correct. So I would phrase it as there's a, yeah. Right. That's right. So the actual time of failure is alpha naught dependent. Yes. Yes, but I could have renormalized that as to a different epsilon. So I usually think of fix alpha naught on a sphere and then pick different epsilons. So if alpha naught is on a sphere, then it's bounded and it's of the same value. It's really the epsilon. But if you picked a larger alpha naught, that's equivalent to having to force yourself to consider smaller epsilons, so that the time of good approximations is sufficiently large. Yeah. In that sense, it's restricted. But what I would usually do is just normalize yourself to be on a sphere and then consider epsilon to actually decide the size of the initial condition itself. So one other way to define what you mean by weakly nonlinear equation is equations whose initial conditions are small. So you can think of scaling the initial condition by epsilon, which is what I did for the first algebraic problem where I didn't have an epsilon, and I scaled it by epsilon to introduce an epsilon. So then I've said, actually, my initial conditions are on a ball of size epsilon. No. I haven't told you how I'm finding omega. Usually you'll find omega through some sort of Fredholm integral condition. And omega will be written as a bounded function of t. Or if it is a powers of t, only valid for some time, which makes sense. I mean, it's like saying e to the t can be written down as its Taylor polynomial, and that's only good for some t. So then it's only good for some time. Yeah. So it's just to point out that there are many ways to skin this cat. You can sort of get the same answer in different ways, fix different kinds of degrees of freedom, and sort of end up at the same answer. at least asymptotically, of the same order. Right? So you could have, I mean, this number might be different with an epsilon squared, but at this level, they look the same. So this is the funny thing about asymptotics. Things don't have to equal 0, they just have to equal epsilon. And then many things can be hidden there. Right? Any other questions? I think that's probably a good place to stop if there are no further questions. All right, great. Oh, one comment, yes. Yeah. It doesn't apply to this one, no, because this is an integrable system. Yeah, but it's also integrable. So it's, I mean, it's completely integrable. Yeah, this ODE is, so it's not even a question. Yes. Precisely, yeah.